So we're in section 12.1. Tangents to circles. When you go a little further, I was just thinking we've talked about tangent when we talked about SOHCAHTOA, sine, cosine, and tangent, and we had talked about the tangent of an angle. The tangent of an angle and two curves intersecting at a point, they are related. And when you go on in math, your pre-calculus teacher or your calculus teacher should talk about how the tangent function is related to what we're talking about with tangents today, because there is a relationship between those two. Tangent to a circle. So what we're talking about, we talked about tangent means that the two things intersect in exactly one point. So let's talk specifically about circles. A tangent to a circle is a line or segment in the plane of the circle that intersects it in exactly one point. So if we draw a picture here, let me grab a circle. And I'm going to draw a tangent. So there's my circle. And we call this the tangent point. So that's what the definition that some of us had, where the two figures intersect in one point on a line. Well, there's that point. We call it the tangent point. And we call the line the tangent line. And if you go on to take calculus, finding tangent lines to curves is an important topic, because a tangent line tells us something about what's going on with the curve at that point. And tangent means to touch in Latin. So that's why they call it a tangent point. All right, so we have one main theorem that we're going to talk about for this section, which we're going to call the tangent theorem. So tangent line intersects a circle in exactly one point. We have a theorem, because that makes a special relationship. The tangent theorem. And I'm going to say and converse. We're going to talk about both together. The tangent theorem tells us that if a line is tangent to a circle, then it is perpendicular to the radius at the tangent point. So that's our special relationship. Tangent line is perpendicular to the radius. So let's draw a picture. There's my circle, and here's my tangent line, like so. There's my tangent point. If I draw in a radius, to that tangent point, the line and the circle make a 90-degree angle. Call this circle O, call that tangent point P, and call this line AB. So in symbols, we'd say line AB is tangent to circle O at P. Well, that means that OP, segment OP, is perpendicular to line AB. So that's a pretty important relationship. The tangent line is perpendicular to the radius. The converse, for a converse, we reverse the if and the then. So we're going to say for the converse, and the picture is the same, if a line or a segment is perpendicular to the radius, perpendicular to the radius of a circle, then it is tangent to the circle at that point. And why don't I say, instead of, I'm going to say on. So the line is intersecting the circle right on the circle. So the basic idea here, the big idea, is that tangent lines are perpendicular to radii. All right, questions? Okay, I'm going to give you a couple of pointers for chapter 12, kind of like we had in chapter 7, when in doubt, write a proportion. In chapter 12, a couple of pointers. All radii are congruent. So remembering that all radii in a circle are congruent can help us solve problems. And in chapter 12, I'm going to say, when in doubt, draw another radius. And usually when we draw another radius, we're going to draw it in a convenient place. But drawing a new radius can help us solve problems. All right, let's look at an example. So I have a circle here. Whoops, I have a circle. There we go. And I'm going to draw a couple of segments here. That intersect outside the circle, and I'm going to draw in a couple of radii. And I'm going to say this angle is 152 degrees, and this is point D, G, and A, and this is X degrees. And I'm going to say that AD and AG or tangent to circle O. Find x. Well, if these two segments are tangent to the circle, what do we know here about the angle that the tangents make with the radius? Well, what did we just say for our theorem? The line is tangent to a circle, then it is perpendicular to the radius. So those angles both have to be 90 degrees. What do all the angles in a four-sided shape add up to? 360. So I know that 90 plus 152 plus 90 plus x has to equal 360. So I add the angles up and subtract from 360. So this is, when I add these two together, this comes out to 332. So x equals 360 minus 332, which equals 28 degrees. So something that you'll see in chapter 12 that happens is a lot of stuff that we talked about previously. All the angles in a quadrilateral add up to 360. We've talked about the Pythagorean Theorem. Lots of different pieces that we've used over the course of the semester we use together in problems that have to do with circles. All right, so let's look at another example. Questions here before we go on. All right, here's our next example. Have a circle. That's a radius. I'm going to call that x. And I'm going to say this piece is 18, and this piece is 24. And we want to find x. So they might have told you that this segment down here, the 24 segment, was tangent to the circle here at this point. So that's another way you might have had this problem set up. Any ideas? Well, we have a right triangle there. So what does that suggest that we might be using here? We might be using the Pythagorean Theorem because we're looking for sides of triangles. Well, if this piece is x, what is this piece? They're both x. Both of them are radii. So this piece is x also. Those are both radii of the circles. Well, that piece is x. What is this whole length? That's x and that's 18. What are they together? 18 plus x. So that whole side is 18 plus x. Well, now we can use a Pythagorean theorem. I'm going to call this side A, this side B, and that would be C. So x squared plus 24 squared equals 18 plus x squared. And remember, 18 plus x squared is 18 plus x times 18 plus x. It's not 18 squared plus x squared. That harms a puppy. So I need to FOIL this out. So x squared plus 24 squared is 576. When I FOIL this out, 18 squared is 324. For my outside, I get 18x. For my inside, I get 18x. So I add those together to get 36x. And for my last, I get x squared. Well, this is nice because I can subtract x squared from both sides, and those x squareds go away. It's nice when we can solve problems without having to do an x squared. And I can subtract 324 from both sides. And I get 36x equals 576 minus 324 is 252. Divide by 36, and I get x equals 7. All right, questions there? Okay, let's look at another example. Kind of a similar setup. So I'm going to have a triangle there, and I have this is 5, this piece is 9, and this is 12. And I'm going to call this segment A, B, and my point here in the middle, center of the circle, is P. And we want to know, is segment AB tangent to the circle? Well, if segment AB is tangent to the circle, what does this angle have to be? If so, then angle PAB is 90 degrees. So if that's the case, then that's a right triangle. So what the question is really asking us is, does a squared plus b squared equal c squared? Does the Pythagorean theorem work for this triangle? If the Pythagorean theorem works, we know it's a right triangle. All right, we know this radius is 5. So what is this piece? That's also a radius. That has to be 5. So this whole side is 14. So what we're trying to figure out here, if I label my sides, that would be A, that would be C, the 14 B, that 14 would be C. That's the longest side. So we want to see if 5 squared plus 12 squared, does that equal 14 squared? That's what we're trying to figure out. Well, this is 25 plus 144, which equals 169. 14 squared is 196. Those are not equal. So this is not a right triangle. So angle PAB is not 90 degrees. So segment AB is not tangent. Because that's not a 90-degree angle. All right, questions there. So this happens a lot in math, where we try to turn math problems into problems that have to do with circles, because circles are nice. And a lot of times we try to turn problems that have to do with circles into problems that have to do with triangles, especially right triangles, because the Pythagorean theorem works for right triangles, and that gives us something to work with in our problem. So a lot of times in math we try to turn math problems into circle problems, and then we try to turn circle problems into triangle problems. So you'll see that quite a bit. All right, one last thing. It's a theorem related to what we were talking about, what we've been talking about. This doesn't have a special name though, so I'm just going to call it a theorem. Our theorem, if two tangents segments to a circle have a common endpoint outside the circle, they are congruent. So our picture for this, we have a circle, we have two tangent segments, like so. This is like the other example that we looked at, but this one doesn't have to do with angles. So there are tangent segments, there are points of tangency. I'm going to call this A, C, and B. So we're saying AC, segment AC, and segment BC are tangent to the circle. What the theorem tells us is that AC, segment AC, is congruent to segment BC. And the way we prove this theorem is we draw in a couple of radii and draw in the segment from the center of the circle to point C, and we would show that those two triangles were congruent. And then we'd use CP/CTC to say that those two tangent segments were congruent. So we're turning the problem that has to do with circles into a problem that has to do with triangles. If we were to go on to prove this. All right, I just want to look at one more example. Questions on this theorem? Okay. We can have a circle. And there's my picture. I'm going to erase some of these extra long segments here. And I'm going to call these points L, M, and N, and call this point O, this point R, and this point P. And the problem tells us the circle is inscribed in the triangle. So before I write any more, let's remember what inscribed means. So if it's inscribed in that triangle, what does that tell us about point O, R, and P? If the circle is inscribed in the triangle, does it touch this side M, N, or N, L, or L, R at any other point? That's what inscribed means. That these points, O, R, and P, are tangent points. The triangle is tangent to the circle. All right, I'm going to label some sides. That's 8. That's 14. And this is 5. We want to find the perimeter of triangle LMN. Well, like we just talked about, inscribed means that those points are tangent points. So the triangle is tangent to the circle at each of those points. Well, here are two tangents that have a common endpoint outside the circle. So what does this segment have to be? How long does that segment have to be? If these two tangents, these are two tangents with a common endpoint outside the circle. What is our theorem? What did our theorem just tell us? Two tangent segments to a circle have a common endpoint outside the circle, then they are congruent. So that has to be 8. Well, here are two tangent segments with a common endpoint out of a segment, outside of the circle. So what does that piece have to be? 5. Two tangent segments over here that have a common endpoint outside the circle. So that part has to be 14. Add them all together. And the perimeter, we get 16 plus 10 plus 18. Sorry, 16 plus 10 plus 28, 54. All right, questions? Okay. Homework? Page 767, 8 through 18 even, and then 22 through 26 even.